Okay, so in this video I'm going to go through the two reactions on question 9 of page 69 at the end of the chapter review questions for civil structures. So we've got two different cases here. We've got a beam and a truss, and in both cases what we're going to do is find the reaction. Now when we do this, the first thing we want to do is we always want to take moments about the pin so that we can find the roller, because the roller is simpler. Right, and by taking moments about the pin, we can multiply that force by 0 and ignore it, because anything multiplied by 0 is 0. So if I go to my working out here, I can show you on the board for the first question. I've chosen a bit of an unusual method for solving this question. So what I've done is I have said, rather than breaking this into components, I've said find the perpendicular distance, because with moments, always what we're interested in is finding the perpendicular distance. Now, there's a good reason why this is not the convention, and I'll talk about that in a second when we go to the answers provided by Copeland. Now, it's important to remember that the textbook is wrong, and that there is errata answers, which I will show later in this video. So to start off with, I have labeled these forces. So I've said here we've got 85, 20 meters away. We've got 100 kilonewtons, 40 meters away, but it's at a 45-degree angle. I haven't labeled that as 45 degrees. You have to know that, unfortunately. And then I've made an assumption that RA is going to be going somewhere in that direction, and I've made an assumption that RB is going to be pushing up, just because it usually is. Now, we're going to find out that for the first time where these assumptions can be wrong. Okay, so I've gone to my formula. My formula says, taking moments clockwise, find the sum of all the moments, which has to be equal to 0, but measuring from point A. So at any point, I could take moments from here, I could take moments from here, but it doesn't matter which point I take moments about, no matter where I take moments, they should be 0, the sum of those moments. Okay, so let's look at our sentence. Now I've got four forces here. I've got RA as a force, 85 kilonewtons as a force, 100 kilonewtons as a force, and RB. Let's have a look. RA, 85, 100, RB. Now you can see I don't really care about the units. Kilonewtons or newtons, it's all the same to me, because ultimately, as long as I'm consistent, my things will work out. The same is true of distances. So if I said pounds, or I think it's foot-pounds, or kips, I think is the term they use in America. Point is, it doesn't matter. Whatever unit I use, as long as it's consistent, we won't have a problem. Okay, so that's true if we're using feet, that's true if we're using pounds, whatever it is, as long as we're consistent, we're happy. Okay. Now, what I've said here is I've said, well, okay, what are the distances? Now, the first force, RA, well, the perpendicular distance of RA to RA is 0. That force is acting through A. So we can just multiply that by 0, and we don't even need to write that. You'll find that Copeland just doesn't even write that force at all. In his answers, he just completely ignores our RA, right? He's not there at all. The next force is 85. So we can see 85 here. Now, I always write it as negative, and then after I look at it, I decide if it's going to be positive or negative. So if we look at 85, it's 20 meters away, and when we push on it, if we push on it using this center point A, if we push on that, we're going to imagine that this wheel is going to go clockwise, right? So it's going to be plus 85 times 20. Now the next point, this is the tricky one, 100 kilonewtons. Now we know it's 100 kilonewtons. I've told you it's at 45 degrees. Now what I said I want to do is I want to find the perpendicular distance. Now in the book they break it into a vertical component and a horizontal component, and that's a really good idea, and I'll talk about that again in a second. But if we look down, if we extend this force all the way for forever, there's a point where its line is going to be as close as possible to point A. Where is the point? So I want you guys as a class to tell me, what point are we as close as we're ever going to get to point A? Now, great, excellent. That is as close as we're ever going to get to point A. That distance is called the perpendicular distance. Now, the question is, how do we find what that perpendicular distance is? Well, okay, I've drawn a picture over here. I've said 20 plus 20 is 40, and I know that it's going to be at 45 degrees because vertically opposite angles are equal. Yeah? Vertically opposite angle, if that's 45 degrees, this is at 45 degrees. So I said, well, if that's 45 degrees, what I need 40 cos 45, because this is the hypotenuse and this is the That's actually sine. You're right. Okay, that should have been sine because it's actually 40 at the hypotenuse and the opposite. I could use 40 here. It doesn't matter. In this particular case, it's fine. So it probably could have been sine. That would have been more accurate if I'd written sine. Anyway, the point is, I happen to know that sine 45 and cos 45 happen to be, and you can't see because the camera glare, 0.707. Right, to 3 decimal places, I happen to know that. So I will just often chuck that in. Okay, so what I'm doing now is, well, I'm going to say the force is 100 kilonewtons, right? I know that. And the distance is 40 cos 45, or 40 sine 45. And I've just written that in there in the brackets. The last force is RB, and RB is 20, 40, 60 meters away. So RB is RB times 60. And I've said here, assume that it's going up, therefore it's going to be anti-clockwise. So what I've done is I've now moved that over to here. I've changed the sign. So what is RB times 60 is now plus or positive 60 RB. And then I've said 85 times 20 is that. 100 times 40 times 0.707 or 40 times cos 45 or 40 times sine 45 is this number. Add those two numbers together, well, you end up getting a really negative number. And the really negative number, we say, well, if 60 RBs equal 1200, what's 1 RB going to cost? Yeah, if I can buy 60 red balloons for $1,200, what's 1 red balloon going to cost? Well, about $20 sounds about right. So it's really important that you use your logic here to check that you haven't made mistakes. To check that, yeah, that sounds plausible. Okay, and now what we've noticed is that number is negative. So whenever we have a negative number, we have to say, well, the number was negative, therefore our assumption was no good, NG being a very common acronym in engineering to say no good, to say that the design is not suitable, and therefore it's in the down direction. Our assumption was up, it wasn't up, so our assumption was wrong, so it obviously has to be down. Now, I'm going to come back to this part of the screen in a second, because that's not normally what we do. Normally what we would do, and when I've marked just recently a whole bunch of papers, I noticed that most students tend to use this method, and that's for good reason. They take some of the forces vertically. So let's have a look. We've got 4 vertical forces. Let's look at our 4 vertical forces. Well, we have RA vertical, we have 85, we have the vertical component of this 100, and we have RB. There we have 4 vertical forces. Now what I've said is that the vertical component of this, the vertical component of that is 100 sine 45 or 100 cos 45. Which, like I said, I know in my head I can do is 70.7, and that's accurate enough for my numbers. Now, if I take the other forces that I know, well, I now know that RB is in fact 18 down. So that's 18.8 down. And I can see 85 down, so that's there. I've got 70 going up, 70.7 going up. So what do I need for that to balance? Well, I need 33.1. Now, I've got the equation there, but you can see. Now, for the horizontal forces, it's even simpler. Right, what I've said simply is 100, and that should actually be 100 cos 45 is the value here, pushing that value, that 100. So let me rephrase that. There's only 2 horizontal forces in this whole diagram. We've got this one here. It's got a horizontal component. 100 has a horizontal component, and RAH. That's it. So if I know the horizontal component of 100, I know the value of RAH. Yeah? If there's a question? Okay, so moving along. So the next part of the question, is not really a problem. But what we can do there is we're going to look at that when we look at the Copeland answers. But what I wanted to point out is there's another way that we can find RAV. What we can do to find RAV is we can also take moments about B. Now, you don't see this happen very often, but it is something you're allowed to do. Now, the reason you don't do it is because it takes a little bit longer, I think, and it's a little bit less intuitive, but it can work. And in fact, I would suggest if you finished early, going over your marks and doing this method is a really good idea. So the same idea, I won't go into it too much detail. What we've got is all of our forces. We've got RAV, we've got 85. I've taken this time around, I haven't used the perpendicular distance. This time I've used composites, the components. So I've said that instead of using 100, I've said 100 sine 45, 100 cos 45. I've just done that here already. But it's important we understand why these are 0. Why this number and this number here are 0. So we'll just go quickly. So from point RB, RA horizontal, the vertical distance is going to be 60 in its perpendicular distance. The horizontal force, though, it's going to be acting through the axis of the beam. So its perpendicular distance is going to be 0. So that's why when I've written RAH, I've multiplied by 0. This one here is pretty obvious. 85 times 40, that's its perpendicular distance. Whereas here we have 100. Well, we need its perpendicular distance from B. Now, we could just measure it or figure it out, but we're not going to do that. Instead, we're going to say, we've already broken it up into components, so we're just going to stick with components. We've said that this component, this 100 is made up of a 70.7 up and 70.7 going to the right. Now, I had a student ask, how do you know it's up and how do you know it's to the right? Well, have a look at the 100. Is it going more up or more down? More up, right? Is it going more left or more right? More to the right. So that's how you know what its components are going to be. So the 70.7 up, well, that's 20 meters away perpendicularly. And the stuff that's going through the axis, well, we've already talked about that. It's going to be passing through the beam, so we can ignore it because its perpendicular distance is 0. So that should give you an idea of how we use that method, and that gives us the same answer, which is a good check. Okay, I'm now going to go to Copeland's answers, and we can see that we've got all of the same things here. Now, like I've already mentioned, he just completely ignores RA from his initial equation. Whoops. He completely ignores RA. He just goes straight to the 85. He breaks it up into components, and again, he completely ignores this 100 cos 45. Completely ignores it because it's multiplied by 0. Then he does RB minus 60. Yep, that's fine. Then, once he's done that, what he does next, the part that we hadn't got to, he says he finds the equation. Now, he does it with more of a calculation than I like to sort of draw a little drawing. But what's important is that he finds the value of RA. Now, he does interchange between RA and RR because this is on the right-hand side. Sorry. Yeah, that is confusing. I can't, yeah, that really should be RA. Anyway, so he says RA is, he uses Pythagoras' theorem. I'm going to assume everyone knows that. He then uses trigonometry to find it. Now, obviously, you can't type this into the calculator. That's not going to work for you. So all we have to do is hit the tan inverse button. And more effectively, the term that you use is arctan. If you're using Excel, it's ATAN, A-T-A-N, 4 letters, A-T-A-N. That's how you do it on Excel. Or if you type into Google, that's how you'll find it. Just be sure that you don't mix up radians and degrees. But tan is opposite, and always remember that tan is opposite over adjacent. So he's written his answers here. Okay. I'm going to do the other one in another video, but the other video should be shorter than this one.